And now, without further delay, it is my pleasure to introduce Michael Haggerty and Joel Swenson.
All right, thanks everyone. Being the last talk of the day before we hear from the governor, we'll try and keep it exciting for everyone. I want to first express gratitude and thank you to the planning committee for the conference. Great conference. Looking forward to the rest of it tomorrow and the discussions going on this evening. So I know this morning we talked a lot about, you heard a lot about collaboration, relationships. I'll take that and say that that certainly applies to the project that my colleague Joel and I are going to talk about here. So with that, we'll get going. I'm Mike Haggerty. I'll talk about the first part of the project, give a little bit of background, talk a little bit about risk, and then my colleague Joel Swenson is going to talk about how we transferred some of the aspects of risk management from the design side back over into the actual implementation of construction. And I think one of the things that is true of any of the projects that we are involved with as a profession is that you're interacting with the ground one way or the other. And when you interact with the ground, there's a certain amount of unknown and variability and risk that has to be contended with. And so how you do that can be handled in a multitude of ways. The project that we're going to talk about, we'll talk about at a high level what were some of those key things related to the project, and then how did we carry that through to construction, because we all know construction never goes exactly like you think it's going to go during design. So I'll talk about project background, risk management, and then I'll hand it over to Joel for instrumentation and some of the actual data analysis. So Stormwater Storage Facility, SSF, what is that? Essentially, this is a hydraulically driven project. Some of you may have heard this morning, we have another colleague, Brandon Barnes, gave a presentation on a project out in Valley City. He was a key component of this project team as well, but this was a hydraulics project in the downtown Minneapolis area, with the client being the Minnesota Department of Transportation. So where is this project? Where is this project we're going to talk about? It's just south of downtown. You can see in the image here, downtown Minneapolis circled in the background. This is looking north, so looking straight up the I-35W corridor, which is a major commerce and commuting corridor for the Twin Cities. Lots and lots of traffic on a daily basis. And that in the system here, how it handles stormwater is, so any stormwater collected in a near surface system south of 39th Street, and then once you hit 39th Street, there's a series of deep shafts that go and convey through a deep tunnel out to the Mississippi River in a direct route. And so our project is just south of that 39th Street shaft, where there's a low area in the highway alignment. It's a very constrained space. This is the great thing is that when you fly into MSP, if you're coming in from the northwest, you got a great view right down that corridor. Some pictures we've taken on the plane, but it gives you an idea just what that corridor looks like. And then that picture on the right, that was during construction. This is a very constrained space. But essentially the root of the problem was that this watershed that drains during precipitation events, when under certain circumstances or certain magnitude of events, there is a potential for flooding that occurs along the freeway. And that flooding essentially can bring highway traffic to a stop. And so this area, this drainage area, this a little over 5 square miles, well, most of it can drain just fine. There's a piece where the project area is where we have issues with the amount of storage that's available. And Federal Highway had told Minnesota DOT that they needed to have about a 10-year, 24-hour magnitude event storage. And we came up with a solution that was a little bit less than that. We'll talk about that, but important to remember this is a hydraulic project. On the left side here is the discharge out to the Mississippi River. And so what are the impacts of the flooding at this location? Total gridlock. And this doesn't happen all the time. It doesn't happen every month, but it does happen on a frequent enough basis in the past that it was a major issue. And like I said, the original intent was to have enough capacity to take a 10-year, 24-hour event. What we did and what we came up with as a design team was to have 14 acre-feet of storage in place. 14 acre-feet is about 4.5 million gallons of water, or roughly about a little over 200 swimming pools worth of storage. So the whole intent is to provide some of that storage capacity when storms hit in the right magnitude to prevent some of the impacts that historically have happened with traffic. What this looks like in concept, this is it. You can't see it anymore, it's all underground, but essentially it looks like it's 6 sequential shafts that are interconnected. And when you look at it, that pipe that's in the median there, that's how current stormwater is carried to the north, to those deep tunnel shafts. And essentially there's a diversion that goes through the first cells. We'll refer to the cell on the south as cell 1, on the north as cell 6. And so when water comes through under normal conditions or low water amounts, it passes right through that low area. It continues on in the median. But in storm events, what happens is when that water hits that first cell, cell 1, it hits a elevation that will go through a double-sided weir and spill over into the cells, the shafts, and essentially fill equally across the way. So this sort of project presents a number of geotechnical challenges. A hydraulic project for the need, but there's a lot of geotechnical challenges, and there's a lot of needs to understand how do we manage those things through design and through construction. Minnesota DOT has a few different types of alternative delivery. They have CMGC, Construction Manager General Contractor, and they also have design build. And so on major projects, a lot of times they will assess what sort of delivery do they want to do if it's not going to be a design bid build. In this particular case, they decided to go CMGC. And the reason they wanted to go CMGC was because they really needed a team that could collaborate through options during design. When they put this out to bid, there was 4 options on the table, and CMGC would allow MnDOT to contract directly with a design team and contract directly with a contractor team in kind of an early contractor involvement format, with the expectation that an entire team would collaborate through the design and iterate on some of the options, really because they knew that given the underground nature and the geotechnical risk, selection of construction methodology would have a great impact on cost and risk. So that was what the delivery method they chose, which meant there was a very collaborative spirit. You'll hear the word collaboration thrown around a lot of times with alternative delivery. For the CMGC project, we had MnDOT as the owner. It was a joint venture of Kramer Construction and Nicholson doing the contractor side and providing early contractor involvement. And then the design team, which the key partners were Barr and TKDA and Brierly Associates. A number of third-party stakeholders that had to be engaged with this as well, and not only engaged during the design process, but also some of the monitoring was to make sure we weren't negatively impacting any of the third parties adjacent to the project. So this is just to give you a sense again on the hydraulics piece. Like I said before, you're looking at cell 1 on the right, cell 2 in the middle there. The water would come in during low flow. It hits that structure you kind of see. That's a 2-sided weir that allows for spillover. And then all of these tanks are connected in such a way that 14 acre-feet is available to storage. That's what it looked like in design. We used BIM 360, and again, we had a very collaborative effort with all the design teams to develop this in 3D and then cut our sections from here. This is what it looks like when it was actually constructed. This is the 2-sided weir. These cells are about 90 feet deep, 42-foot diameter, and they were constructed through diaphragm wall construction techniques, which we'll talk about in just a second. And then they have an interior liner wall as well that was cast in place. So they're extremely robust, which Joel can show on some of the data too. So as a geotechnical engineer, now that we've got some of the background, the other piece that's important to understand is the geology of the site and the geology of the Twin Cities and how that impacts control of risk, decision of constructability of the site. So when you look at the typical layer cake through the Twin Cities, there's glacial drift, glacial alluvial deposits that occur up top. Then as you go down the first bedrock, you will oftentimes hit, not everywhere, but oftentimes hit is the Platteville limestone. Serves as a great competent layer when you first go down. And then beneath that limestone is a thin layer of Glenwood shale, which is an aquitard, and then you get into the St. Peter sandstone. And when the cities of both Minneapolis and St. Paul were first developed, that St. Peter sandstone is heavily, easily erodible. It's very strong in compression, but very easy to carve out or to mine or to dig tunnels in. And so when the city started to get built up, it was very elevation, gravity beneficial to handle stormwater, to dig out tunnels and have those come out of the Mississippi River. So most of the stormwater drainage systems in the Twin Cities are like that. But a couple of the things that are important is that where you construct in the St. Peter, when that plat fill's there, it serves as a good carrying unit but you get these glacial carves, these valleys. And when you get the valleys, you get intermixing of the groundwater table, and you get some different soils than what you expect that drive a need to identify that. So we went to this project, and this was all while we were still talking about how do we build these things. We had competing different historical information on the geology. This map here shows a couple of different outlines of the extent of bedrock in the area. The project extent is on that yellow line there. And what we had was from 79, we showed that the top of the Platteville limestone came right through our project, and then that map was revised. In 89, it showed that all of our project area would have that Platteville limestone. And so when we did our geotechnical investigation, that started to dictate what we thought we were going to see and how we are going to shape out our cells. This is hard to see, but the things I wanted to note here is that this was the actual borings we did, and what we found was, go back to that last slide, the 1979 extents were indeed correct. That was what we had at our site. And so the area of where our cells needed to go were in one of these glacial grooves, which was beneficial from an excavation standpoint, but it meant we had to deal with those particular soils and how we were going to handle that. It also meant, we did some pump tests here, there's a tremendous amount of hydraulic communication between the St. Peter sandstone and the alluvial material. So high groundwater table, there's a blue line there. Hard to see that, but elevation-wise, about 817 to 820. The highway grade on 35W in this area is right around 824, 825. So we had very high groundwater table, and dewatering this to completely dewater the excavation or whatever it was going to be was extremely impractical. So knew we were going to have to construct in a high groundwater table. There's a number of different things with regards to this project we could talk about for risk, but the two that I'll lay out and kind of sets up some of our instrumentation is management of the groundwater pressures. Like I said, high groundwater table, we weren't going to get rid of it, totally impractical, too cost prohibitive, and then the geologic conditions and how that impacted the constructability or the construction technique we used. Excuse me, this is a schematic of the different steps of construction. So when we were talking with the contractor, we did decide early on it was going to be some form of diaphragm wall construction. All that is it allows us to build from a platform, dig straight down with a large cutter head, and then slurry that in place and essentially create the walls underground. Serves as a cutoff, and then we can excavate out the interior soils. But along the way is control of the groundwater pressures as we go. So high groundwater table, you can see on stage 2 there, that's really building the diaphragm walls from the surface, so those are in place. And then when we get to stage 3, we wanted to put wells in to depressurize, not completely dewater, but depressurize to a point where we could control excavation and sequentially do that in a safe, effective manner. Phase 4 is when we're doing that sequential excavation. And because of the risk on this project, there was some terms written right into the contract that require the contractor to achieve a certain amount of depressurization before they could continue along with their excavation. So that was one way we were handling risk. Stage 5, we get to a point where those wells are turned on, and we really need those to be on constantly before we get to the bottom of the excavation. As I mentioned, the cell open area is about 90 feet deep. Those diaphragm walls are about 110 feet, so we had a bit of a cutoff effect on the bottom that we were utilizing. Get to stage 6, that's our critical point in the project from a risk standpoint. At that point, the wells have to be on. If the wells are not on, we lose control of the hole. We would have heave in a very quick fashion at the bottom of the hole, and so there was a lot of redundancies built in there. And then stage 7, we cast in the slab that structurally supports those pressures. And then 8, we come up with some liner wells. So that was the sequence of construction. But knowing how the water was behaving during all those things was incredibly important. So what do we do about that? We had a system of depressurization wells. And so after the diaphragm wells were installed, there was wells put along on the outskirts of each of those cells. And then we had a number of pump tests, and the contractor was required to perform pump tests before excavating to show that they were performing. They did have to redevelop some of those wells along the way, and in some occasions we had to add another pump on the interior of the cell just to create enough control for the contractor. But this was discussed ahead of time. Once the wells were installed, there was a need, because of the risk component, to make sure we had online backup power, so that if there was ever a storm that knocked out mainline power, there's an automatic switch over to generators to be able to power these things and not lose the construction at a critical point. That was all identified during the design phase and then costed out by the contractor and the owner together through their costing process for that delivery method. Specifically for the depressurization, I mentioned we had that in the contract. It's the first time I've seen that where we've put we had specific pressurization goals that the contractor had to show that they met before they could continue with their excavation sequencing. So everyone was extremely interested in the instrumentation of the dewatering, and we had a multitude of vibrating wire piezometers at the tips of these different cells, so we had redundancy in the system, and then we had these things, the data actually hooked up so it could be viewed externally by all the stakeholders, and there was times when they might lose a pump, just one pump or something, and we might see it on the monitoring before they realize it on site, just because the response was so fast given the amount of head there. The truth test was when they got to the bottom. This is a picture of when the bottom was completely excavated out, and the floor was not in yet. And so we, as an experiment, the contractor wanted to see what happens, how fast does the water come up if some of the pumps start to lose. And they had control and they had redundancy, so we could do it in a controlled fashion. And I would say it was probably within 20 minutes you could start to see water seep up. So turn the pumps back on, gave everybody a good sense on what sort of level of time they were looking at, but it was a great test to confirm what those risks were and have the instrumentation tell us everything that we thought was happening was indeed happening. So then the other thing was the ground conditions, and how do we fit these cells into the ground in a meaningful way and have a construction sequence that allows us to manage that. You can see from the aerial drone footage, this was immediately adjacent to traffic, live traffic, and there was a major construction project going on adjacent to this one, and so there was a lot of interactions between those projects. Early on through the design phase, contractor identified, and we talked about whether we wanted to have shared walls between the cell walls, because you can do that. We made the decision to not do that because it would allow us to be able to sequence more effectively as we jump from cell to cell without having that longer cure time and just some of the limitations if there was a little bit of differential settlement. It wouldn't put as much risk back into what a shared wall would be. So the decision was made, separate them all so they're independent structures, they can carry the stresses of the soils fairly well, and then what that meant is we had to make connections between those cells, and we had a connection at the top and a connection at the bottom. But before we even put in the diaphragm walls, that meant we had to jet grout. So contractor came in and jet grouted to try and precondition the soils, and then once the cells were constructed, we hand dug between one cell to the other. But that was an efficiency, a risk control that was identified through the design phase. The diaphragm wall construction was really done through a couple of techniques. There's a clamshell option, clamshell bucket, where you can pick up softer soils and excavate, and then you have a hydrophrase, which is a cutting wheel, multiple cutting wheels that will actually grind away at denser material or rock, and then you put a slurry in. Slurry holds the excavate or the slot open, and then you can tremie pump concrete in there to create that exterior wall. And so those are the methodologies used. It worked out great because it allows us to work from above that groundwater table, but get that a high level of control in place on the type of concrete that we're using and the curing of it to know that our walls are going to be good. Side note, COVID hit in the middle of this project. The crews that operate the hydrophrase are very specialized and there was a delay a little bit on the project because one of the crews was in Europe and could not get back to the U.S. to work on the project. But give you a sense on what this looked like at the bottom when we made those connections, you can see some of the jet grout on the left. So jet grouting, we're drilling down and injecting grout before anything else is done to try and solidify the soil and create a little bit of a water cutoff. You got to remember, there's about 80 to 90 feet ahead above where this is at. So we didn't want to have the diaphragm wall in place and then poke a hole in it and we lose all this ground. So that was the reason for the preconditioning. But we were able to punch through successfully, control the water inflow, and then do cast-in-place connections between this. The other thing that was a part of this project was, you see these openings, they're about 10 feet wide. Oftentimes you get sediment in a structure, a storm structure like this, it's possible. So we worked with MnDOT maintenance to identify how can we get sediment out in the event that it comes in there. So all the floors are sloping to the middle, and then all of the 6 structures, there's a slope that goes to the north. So we're trying to consolidate where any of that sediment would come. In the event they needed to, there's access. You could drop like an electric skid steer or gas-powered skid steer in there, and those widths are there to allow for passage of some of that maintenance equipment. I talked about the clamshell and the hydrophrase. You're looking at some of the geotechnical summary of the borings here. The blue and the red are areas where we had softer soils or looser soils. And so that was identified during design that clamshell could be used. So that was incorporated into the costing from the contractor. And then beneath that, we got into much stiffer alluvial soils. And so that was the identified transition to go into the hydrophrase and do the excavation for the hydrophrase at that point. And that allowed the contractor to figure out what that efficiency was going to be, what the costing was going to be for each of those things. And that concept model carried all the way through any of the costing exercises and the risk. Along with that was trying to identify, is there boulders in there? Boulders even, we oftentimes think about like a geotechnical baseline report where there's boulders and you're trying to quantify how many, what can the contractor assume in their bid. In our case, we didn't try and quantify the number of boulders, but we tried to quantify zones where we believe they existed. And this is a picture of some of those as they came up with the hydrophrase, and those would wear teeth out in a hurry when they had to deal with some of those things. So that did come up. Even with all of the best planning, there's still things that come up, and so how do you get through that? So those are two of the things from the standpoint of risk as far as conditions encountered and conditions planned for and designed. What did that mean on the contract side, especially on CMGC delivery? So this was a diagram we worked up just to try and lay out how it was handled on this particular project. And you can see on the investigation side, or RID, reference information documents, all of our geotechnical information, some of the baseline monitoring that was done ahead of the design that was available to the contractor, and then there was a risk registry process that was run through during the design phase that fed into some of the costing exercises the contractor did. So then when you get into the contract itself, for this particular project, we did a geotechnical interpretive report, much like a GBR, but really that was to define some of the things that were anticipated to be in the ground for the contractor to use, and this was done collaboratively with the contractor, but it became a baseline for their costing exercises or triggers to, say, open up risk allocation dollars if they hit unexpected conditions. We tried to include things into the special provisions, like the pore pressure requirements, and then during the costing exercises, the contractor and the owner would go through the risk pool items. And then when you get into construction, yep, there's still a possibility of a differing site condition. When you talk to a construction lawyer, they'll say differing site conditions and unexpected utilities, two of the biggest items for claims. So there's still a mechanism to go through that, but ideally, we've handled it through a bunch of different ways. If indeed there is a differing site condition, then there's a way for the contractor to handle that. What we've tried to do in this particular type of procurement is define triggers so that if something is exceeded, a ground condition, boulders, let's use that as an example, that then is an agreed upon item before construction to say, yep, you're exceeding this, that's going to open up some of the risk allocation dollars. And then eventually you still have options to go to a resolution of a claim like arbitration. But I could say on this project, what happened early on was a really good spirit of collaboration. There's certainly challenges during construction, but that collaboration kind of carried through on the construction to make it successful. And so those are some of the things we did to manage risk on the design side leading up into construction. And my colleague Joel is going to talk about a lot of the instrumentation that was implemented during the construction of the project.
Thank you, Mike. Hello, everyone. So for this project, there was quite an intense instrumentation and monitoring project. I'll walk you through that. One thing to note is we started as part of the design considering and knowing that instrumentation was going to be a part of it to reduce the risks. So it wasn't an afterthought. It was a part of the initial planning stages. So Mike's shown this photo before, and we have the project area highlighted there in the orange rectangle, and we have the sound wall above that orange upslope of the orange trapezoid, and we have the slope that was the old inslope of 35, and then we have the I-35 northbound lanes there. So in this photo, we have three things that we need to monitor for to protect the public and the contractor. One is the soil nail wall and the residences behind that soil nail wall. Two, the soil nail wall itself. Three, the groundwater pressures that Mike had talked about. And then actually fourth, the pavement surface. So I'll go through each one of these and we'll show you how we instrumented them, the results from the work, and showing you that it was a success at the end. So in order to scope a monitoring project, you need somewhere to start. And here we used 3D element modeling or 3D finite element modeling to determine where the displacements would occur. So those displacements are what the residences would see or they would feel along 35 as you're driving along the road. So in order to reduce that risk of people being impacted through the construction project, we zeroed in on the color contouring here. So if you're looking on the right-hand side, you see greens. That's about a ½ inch of vertical displacement downward, and that's where the soil nail wall would be in the work platform. In the middle of the screen, you see the green arrows at the base of the excavation. Those were heaved. That was another ½ inch. And then at the reds on the left-hand side, that would be dropping, lowering of 35. And this is all due just to dewatering, removing 100 feet of 90 feet of water. So a dewatering project, as some of you may know, can influence not only your project site, but a long ways away from your project site as well. So starting with this, one can start to think about what sensor selection, reporting frequency, and how to visualize and how to analyze that data. So how does one monitor a soil nail wall during construction? Because you've got to build the wall and monitor at the same time. So with that, there's monitoring prisms across the sound wall. And then as the soil nail wall is installed, we're putting sensors on soil nails as they're going in, and then prisms on the concrete face. On the right-hand side of the project, you can see it's quite cluttered. So how can you use a total station to shoot all those prisms? How do you collect your data out of there? It's very challenging, given the fact that you're working in such a close proximity with the contractor and things can get hit. One thing to note here, again, I'll touch on this. This is one of Mike's photos from earlier, is the distance between the hydrophrase and the left-hand photo and the base of the soil nail wall. There's not a lot of space there, so I'll come back to that in a moment. So looking top down, I'll start referencing the photo on the right for the purposes of the diagrams we'll be showing you next. So looking at chamber 3, it was my favorite chamber, if I had to pick one. There's a lot happening here. So in the middle photo, you see it's a black and white photo. As you can see the soil nails extending under the street, 2nd Avenue, going left to right in the right photo. There's 3 cylinders, horizontal cylinders in that photo or the image, and those are utilities, gas lines, water lines, and such. So in our analyses in the design, you're allowed deflection within the soil nail wall itself to budge, to move laterally about 1 inch. Well, if you go further than that, you can take out those utilities at the ends of the project because they become under strain. So how do you watch for that? I'll start to show you some information how we did that, but it's a consideration. So again, if that soil nail wall were to move, we'd have a lot of problems. So a slice through chamber 3, I got a diagram on the right. It's really busy, and it's going to just work with me on this. The yellow dots up on the top are the survey prisms we measured for displacement. The vertical blue line is a shape array. It's an electric garden hose with a bunch of cell phone sensors on it, essentially, to measure tilt. So you can measure ground, how much the ground moves. And then the blue dot in the bottom of the chamber is those vibrating wire piezometers that Mike talked about. And they measure water pressure in the ground. So with those three items, we can start to measure the impacts of what the construction is doing. So you get a very confusing plot like this, but hang on. There's a soil nail wall construction diagram or gray box highlighting when the soil nail wall was occurring, starting back in September 2019. Then it gets to that first white box. But right at December 2019, you'll see a lot of those black lines go vertical. And what happened there was in that small space I talked about earlier between the hydrophrase and the bottom of the soil nail wall, the contractor decided to install sheeting to stiffen up the soil there as the hydrophrase is going to come in and start removing that ground. Well, that vibratory installation of the sheet piles caused a lot of horizontal displacement. I got the red arrow there to show you where the design limit was for lateral displacement of the soil nail wall. So they shot right past that, up to 4 inches or 5 inches. So the top two lines that are more jagged are the prisms. The two bottom lines, or there's three SAA lines, there's segments along there. And you can see how that wall really wanted to take off to the left. Furthermore, we got the piezometer I was talking about a little earlier at elevation 711. And you can see no impact due to their triangular dewatering program out by March 2020, which is about the second gray box. When you get to the pink boxes, that's where we saw those model displacements from earlier, the ½ inch here and an inch over there. Well, we can see there's not much impact on the soil nail wall itself. When that blue line drops down 90-some feet in total head, the black lines stay horizontal. So, success. Measured some things, no one got hurt. And then the next component to this cross-section was instrumenting those soil nails that went behind the concrete soil nail wall. We could put strain gauges on those sensors as they're installed, and they're grounded in place. So you got little bathroom scales on those tendons. And then I got some green dots there showing some other vertically placed, I'll call them earth pressure cells, but bathroom scales essentially too. You can feel the pressure of the ground. So I'll explain why it's on the bottom of this plot in a second, but essentially what we could see at that December 2019 timeframe is that when the contractor decided to install those sheeting, we could read this data and understand that the wall actually was going along for the ride. So it was very, very powerful to install or vibrate the bottom of a retaining wall in an active construction site. So when you start to place that data on top of the previous data, if you have perfectly lined up axes, a story starts to be told. And this is where the power of instrumentation and monitoring really comes out. You can start to explain things that you'd have maybe seen as a crack on a wall or a crack in the soil. So without getting into too much detail on this, but it's very interesting to me, is that the picture on the right was a monitoring, or no, it was a dewatering well. And they're having troubles with getting it to install it. So again, some more vibratory work was happening maybe 60, 70 feet down on the ground, and that still showed up in the upper plot. I got the blue arrows radiating from that photo to the points in the plot showing, hey, there was still a ½ inch of movement from trying to install a well or develop a well 70 feet down, or maybe it was 70, 80 feet down, that would manifest itself up in the soil nail wall. So in vertical walls like this, it's very challenging to not disturb it if you're going to work at the toe. So some lessons learned out of this was be very careful when working at the toe of the wall. So that was the soil nail wall. The next spot was the depressurization program that Mike spoke about. We had each of those yellow arrows points to a depressurization well, and then within the chamber, we had installed our vibrating wire piezometers with cabling and such, which is a challenge in itself. So for the sake of this plot, there's two blue dots on the bottom of the screen showing you some depressurization results from those sensors specifically. And as Mike talked about, it was a contractual obligation for the contractor to make sure they met these depressurization goals. But you can see from the plot for the first pink zone, the cell 3 excavation, they had played with the depressurization program a little bit beforehand, but when they started getting after excavation in cell 3, they just lowered it and kept it there the whole time. So they met their goal through the duration of the project. And then what's really neat is you can start to see around the middle of the plot, so you start seeing black spikes pop up. The biggest one in the middle is where the contractor decided to do the field test to see if they could get in the basket fast enough before liquefaction took off on them, as they started watching the water come up out of the ground in 20 minutes being turned off. But this was the most watched component of the program, as it did have the most impact, immediate impact on the contractor's health and safety. So now we're looking over to 35, the actual interstate in use. So the challenge with 35 was that if the contractor encountered boulders and such, or other unforeseen conditions what could cause trench collapse, or if they had a loss of depressurization system event, you could have a loss of ground loss under the interstate. And then you need to understand how bad is the interstate impacted, and should they shut it down? So we monitored where the traffic is moving up. See the right-hand side photo there with the trucks moving north. We measured that with automated motorized total stations as well. And in the middle is one of my favorite pieces of equipment I saw on the site, and that's a chisel. So when the clamshell would encounter a boulder within those deep excavations or the hydrophase, they'd get the boulder or the chisel out, which they just drop into the slurry to pound up the boulders at depth, and then they could chew it up after that. So, novel approach. So starting to look at the 35W, you see the yellow dots on the left-hand side. Those are reflectorless pavement shots using a total station. And then, so I'll plot that next. And the vertical yellow line is another one of those shape arrays adjacent, so in between along the shoulder line of 35. So a concern here was that the different types of excavation processes could have result in that ground loss, but we wanted to see if one was better than the other. So on the first gray box on the left-hand side of the plot, that's clamshell. You could see that the black lines didn't show much movement. We had maybe an inch of movement in several spots along some sensors. But the hydrophase is when you get about halfway down, they would use that tool, and that would be more of a grinding technique to excavation, and that showed substantial more movement in the ground in the sensors adjacent to the excavation technique. So that's pretty interesting to see. And then as you moved along through the depressurization program, we could see that right about the first red box where the pink line is at, that when they dropped the water, you could see that there wasn't a great amount of influence in the lateral displacement of the system. Now all the stuff in the middle is, as the sensors jostling around in the hole adjacent to the excavation, you get a lot of noise. But then we can plot up the black dots on this plot to show how much the interstate actually lowered due to the depressurization program. And you see those are charging and trying out the system. They were causing settlement within 35. But, and as it would turn the system back on, as the blue line would go up and down on the left-hand side of that plot, the ground didn't rebound, it stayed down. And it continued to stay down throughout the project after they lowered the groundwater. So 35 lowered about a quarter inch or so from the results of this drop in the water in the depressurization program. So I'm going to end with a bunch of rapid fire slides here. The component, so we were talking about how the public was potentially impacted and how do we monitor for those risks. But now this turns into instrumenting the actual diaphragm wall that Mike talked about earlier. So there's a north cage and a south cage on this chamber 3. And what a cage is on the right-hand side of the photo, you'll see an H-pile. And on the H-pile, we installed cables that ran the whole length of the H-pile. It's about 90 feet long. And we could place sensors at certain intervals to measure strain within the concrete. So in the middle photo, you can see the whole pile assembled, and there's a wire rope extending from top to bottom with sensors dangling on it. So they could lower that into the bentonite slurry and then trim in concrete. So we had sensors along the whole length of each side of the chamber. So during the design, the concern was that if you're excavating one cell adjacent to another cell that's already got the D-wall installed, the ground might want to rotate or lean out towards the excavation and thereby cracking it. We're constructing water holding facilities, and we don't want our facilities to crack. So what this was meant to do was investigate how much cracking is it going to occur, or will occur, may occur, in those diaphragm walls in each chamber. So imagine with me, we're looking at a time when both cages are both installed into the grout and the concrete has been poured. So now they're just sitting there and the ground has not been excavated in the middle of the chamber. So as we start clicking through time, and I'll show the schematic as the ground lowers to see what the stress changes are through color contouring. So the groundwater pressure drops down about 80 feet, and we can see a max microstrain about 30, and 30 is a very small number. And the other plots are showing hundreds. So then we start stepping through, you can start to see that the inside of the chamber is in compression. The outside of the chamber is in tension. And each chamber is about as wide as one of these panels I'm standing in here, about 4 feet. So you step down again, you get more compression up top and more tension on top. And you get down to the bottom of the excavation, it's got about 30 microstrain. It's not a lot. So a lot of that hoop stress is really small within the chamber itself because you're trying to squeeze an egg. So then before the liner, we might not have touched this earlier, there is the diaphragm wall, and then inside there's an additional liner constructed. We called it the ACI 350 liner. And that was essentially a curtain hung on inside, or doweled and poured in place, but inside the 4-foot wall. So we can start backing up. Hey, when you start putting that on, we can start seeing this compression, again, develop within the chamber as you stepped up. But all in all, the max strain during all this is 90 microstrain, which is very small. Just during the day, the sun would heat and cool the concrete about 30 to 40 microstrain. Just as the sun's touching something, heating up, it's going to cool down. It experienced a little bit of strain itself. So, I mean, hats off to a sudden great construction to create such a stout system. So in conclusion, the SSF was constructed to minimize stormwater impacts in 35 and those risks that come along with it. The assets monitored were a soil nail wall, the sound wall, and then the utilities behind there. We saw that working at the toe of that soil nail wall and with vibratory equipment can really impact performance of the soil nail wall. The groundwater depressurization program was the most sought after and simplest components of the project, but that one had immediate impacts should it have failed on the contractor. So if it's one thing we got to call on, it was, hey, can you explain what's happening here with the depressurization program? The third thing was excavation of the chambers did not impact one another laterally, and the groundwater depressurization program caused about 1/3 of an inch of fall in the 35W bridge. Not bridge, roadway. Otherwise, in the D-wall vertical strain system that we had set up to monitor performed extremely well, and it's really interesting to see something that's not done very much in the world. So, thank you.
So we have a couple minutes. If there's any questions, it's really hard to see from here. So, see one up front. Yeah, go ahead. Sure. So the question was, what's the biggest storm event that has occurred since this structure came online? So, substantial completion was conducted or completed last May. So it's really only had one season. One season has been pretty dry so far. MnDOT has operated it. We didn't get into it here, but a whole other component of it is there's a lift station on one end of this it's got sensors embedded into it to not only trigger the traffic management center to be able to put road language up warning of impending flooding, because it doesn't prevent all flooding in a significant event, but it also allows the pump system to discharge the water from the stored cells into the mainline system after the mainline system has evacuated any of its water. So, so I can't answer the specific size yet, but the 14 acre-feet I could say is equivalent to, I think it's about a seven-year, 24-hour event from a magnitude standpoint. Other questions? All right. Seeing none, I think we're good. So thank you, and appreciate your attention this afternoon.